Hey, this lesson 9-2, first one of the semester. Let's dive right in. We're talking about similar figures. Now, mathematically speaking, the word similar is a little bit vague in everyday conversation. If I ask the question, are you and I similar? Well, we are similar in some ways. We're not similar in other ways. And so to answer the question, are we similar, period, really is a matter of how you define similarity. And people can use that word differently in different contexts, and it's okay. But in a mathematical context, it's not okay. We need to have very precise meanings for words, and we do for the word similar. To say that figures are similar means something very precise. We got to learn about that. So I've got three stick figures here, and they all certainly look similar to each other in this kind of vague way. All right, but I have recorded some measurements. Let's just say the units are millimeters of the arm, the torso, and the leg of each of these three stick figures. And so this first stick figure here, his arm is 8 millimeters, torso is 10 millimeters, leg is 12 millimeters, and so on the measurements for the others. Now, when I compare the corresponding measurements between two figures, as we can see here in red, right down here, I have divided the arm length of this middle stick figure by the arm length of the first stick figure. 12 divided by 8 is 1.5, to see that the middle figure's arm length is 1.5 times as much as the first figure's arm length. And then by doing the other corresponding length divisions, I see that each measure of this stick figure in the middle is exactly 1.5 times as long as the corresponding length from the first stick figure. Oh, no, wait, that's not right. The third measure is not 1.5, is it? It's 1.6 repeating, okay? So these figures are not mathematically similar to each other. In order for figures to be similar, one requirement for the mathematical definition of that word is that all of the ratios of the corresponding length measures must all be exactly the same. In other words, any length measure you take from one must be the same multiple of its corresponding length measure as any other measure you take from the one. Always the same multiple, okay? And we see the multiples here are 1.5, 1.5, 1.6 repeating. So those figures are not similar. They're close, but they're not. Likewise, between the second and the third figures, I see that the third stick figure's arm length is 3.3 times the middle stick figure's arm length, the torso length 3.3 repeating times, and then the leg length exactly 3 times. Now listen, when I say the ratios must be exactly the same, I mean exactly the same. Okay, 3.3 repeating is not the same as 3, and 3.3 repeating is not the same as 3.3 non-repeating. Okay, those are different numbers. And when we say they must be the same, we mean exactly the same. Now, if you compare the ratios from the first stick figure's length measures to the third stick figure's length measures, 40 in the arm to 8, 40 divided by 8 is 5, 50 divided by 10 is 5, and then 60 divided by 12 is 5. All of those ratios are the same. So this stick figure, we might say, is 5 times as large as the small one. And so they are similar to each other. Now, it doesn't matter which way you write the ratios, which way you do the division. We could do the division in the opposite direction. 8 divided by 40 instead of 40 divided by 8, we'd get 0.2. And then if we do the other divisions in the opposite direction, we get 0.2, 0.2, 0.2. So it doesn't matter which way you're checking the math, so to speak, as long as the result comes out exactly the same each way. Same for these sets of comparisons up top here in the red and in the green. If I did the red divisions the other way, I would get 0.6 repeating, 0.6 repeating, and then 0.6 not repeating. And so that shows that those first two figures are not similar. Likewise for the greens, if I did those the other way, 12 divided by 40 would be 0.3, 15 divided by 50, 0.3, and then 20 divided by 60 would be 0.3 repeating. Not the same, okay? So you cannot judge mathematically by looking at two figures whether or not they are the same. You've got to have some measurements. But there is one other requirement mathematically for two figures to be considered to be similar to each other. It's not just about the lengths. It's also about something else. Take a look at this small stick figure in the center of the screen now. I'm sure you could come up with a reasonable, not so mathematical, but an easily understood and appreciated reason that everybody else would agree to why that little stick figure in the middle is not similar to any of the three stick figures at the top of the page, right? What's it about? Why is it not similar? Right? It's because the arms on that stick figure are pointing up, and the arms on all the other three stick figures are pointing down. So that clues us in to the other requirement for figures being similar, which is that the angles can't change. None of the angles anywhere can change, right? Wouldn't that be a good mathematical way of describing what's happening here? In that middle stick figure up above, we would say that the angle in that stick figure's underarm, okay, that underarm area between the torso and the underarm is about, it's an acute angle. It looks like it's about 60 degrees. Whereas then when you go to the stick figure down below, the arm is holding up and the angle between the torso and that arm going up is now an obtuse angle, 120 degrees, okay? So those figures are not similar. Now, what about that stick figure over on the right at the bottom of the screen that's tilted over, laying on its side? Well, tilted over, laying on its side doesn't matter, okay? You can spin the figures around. Again, if we just take corresponding length measures and compare them, okay, and we get the same ratio every time, and none of the angles have changed, then the figures would be similar to each other, okay? So down at the bottom of the screen, you don't have to take any of these notes. These are all recorded for you already. But when we get to the next page, we're going to work through some example problems. And again, I remind you, I think really the best way to take these notes is to have a clean copy printed out. If you haven't done that already, if you sort of forgot or you got lazy or you're new to the class, print out the clean copy of the notes and record the notes on your own copy as I'm going through the rest of this lesson. But if you don't have access to a printer, or for whatever reason you can't have a printed clean copy, there will be available a completed copy of the notes also, okay? But before we get on to solving some problems, here's some notes about the meaning of similarity in a geometric context. And in layman's terms, we might say figures are similar if one's a larger version or a smaller version of the other. Kind of like what you do with your phone. When you enlarge or you shrink pictures, you always get similar versions of the original picture, right? You don't skew the picture by making it tall without making it wider at the same time, right? In more precise mathematical terms, as it says at the bottom, two figures are similar only if the ratios of all pairs of corresponding lengths are equal and all corresponding angles are equal. That's the hard and fast requirement, okay? So let's do some problems. First problem, it says triangle DEF. Oh, what's that symbol in there? It kind of looks like a congruent symbol, doesn't it? But it's not a congruent symbol, is it? Because a congruence symbol is two of these things. No, it's one of those things and then with an equals sign beneath it. That's the symbol for congruence. What's here is the symbol for similarity. This tells us triangle DEF is similar to triangle JKL. As with statements about congruent triangles, triangle ABC, congruent to triangle PQR, the order of the letters is significant. It's meaningful. It tells us something very important. It tells us what things correspond to what things, okay? So since triangle DEF is similar to triangle JKL, and I want to know the length of FD, which is over here, okay? Here's a good idea. Let's use some algebra to set up a variable for the length of FD, okay? And what does FD correspond to? See, the names tell us. F and D are the third and first letters in this triangle's name. It must correspond to segment or side LJ in the other triangle. LJ is here. What I like to do is I like to physically connect my variable to the length that it corresponds to from the other triangle. You don't have to do this in your work, but I find it to be a useful tool for guiding myself as I do it so I don't make any mistakes, so you don't make any mistakes, okay? Now, whatever that ratio is, and I don't know what it is because I don't know X, okay? But whatever it is, it has to be equal to, since the triangles are similar, that ratio of those two corresponding lengths must be equal to the ratio of any other pair of corresponding lengths in this picture. So if I can set up another ratio with two actual numbers in it, not variables, but two actual numbers in it, I should be able to solve this equation I have begun for the variable X. So I need two more sides, one from each triangle. They've got to correspond to each other. Well, I only have this side to work with from triangle DEF, and it belongs to, that measure belongs to segment EF. That must correspond to segment KL because of the order of the letters. You see, you must look at the names of the triangles in that statement. There's no way looking at this picture without the names that I've given you. There's no way looking at the picture that you are going to know that EF corresponds to, what does it correspond to? LK. And that DF corresponds to JL. I mean, the triangles, they've been drawn to sort of look almost as if they were equilateral. It's really impossible to judge visually which segment from the first triangle corresponds to which segment from the second triangle. Go by the names, okay? So since I have written the first ratio, x over 325, going from this triangle to that triangle, then I must set up the other ratio in the same direction from here to there, 484 over 300. Now that's a super easy equation to solve, right? We just multiply both sides by 325. And then it's time to pick up the calculator and plug all of this in. And we get what we get. I wish I had an answer in front of me. I don't know. The completed version of these notes will have the answer filled in. I don't have a calculator on me, and I'm not going to try to stop or restart this video or redo it, okay? But putting all that in will calculate the correct answer for us. Yeah, I'm not going to try to do that in my head either, okay? Now, let me say one other thing before I go on to any other examples. I know, because I used to sit where you sit, okay, that the way that I have set up this problem may seem to you to be unnecessarily complicated, overly sophisticated, very math teacherish, and you're not going to do it that way. And you could get away with doing this in a more intuitive way, which I think a lot of you are prone to do. I'm going to describe that way in a little bit, but I'm warning you before I even describe it to you. This more intuitive way, if you depend on it, is not going to help you through some of these other slightly more complicated problems. Okay? Look, I've been where you sit, and I've made this mistake. I've watched teachers solve a problem and thought to myself, why are you making this so complicated? I can already solve this problem, and I've got an easier way to do it. And I then reject the teacher's method of doing it And then later I run into problems where I'm like, how do you do this? He didn't explain how to do this. And then oftentimes a friend would tell me, if you got to do what the teacher said to do. This is how he told us how to do it. If you do it this way, it'll work out. And then I'm like, oh, I guess I should have listened to him. All right. So what's the more intuitive way that I see students do this kind of problem all the time? Well, here it is. Let me erase all of this stuff. And they'll pay attention to the order of the letters. Okay. And they'll say, well, let's see. They'll look at this triangle on the right and they'll see that all of these numbers are smaller than 484. So this is the smaller triangle, and this is the bigger triangle. And so then they'll ask themselves, how many times bigger is the big triangle? Like, is it twice as big, 3 times as big? And so they'll divide the 484 by the 300, okay? And whatever that comes out to be, it comes out to be. And they get a number, and it's going to be a number like 1.61 repeating. It's going to be some nasty number, okay? And so they're already in trouble if they don't hold on to the repeating decimal when they do the rest of the math, which a lot of students don't do. They round in the middle of the problem, then they get an answer which is not exact, and I mark it wrong because I want exact answers all the time, unless I specifically say, give me an answer rounded to the nearest 10th or 100th or whatever. But if you do 484 divided by 300, I think you're going to get this number 1.61 repeating. Okay, now if they can deal with the repeating decimal, they'll say to themselves, all right, so the big triangle is 1.61 repeating times bigger than the little triangle. And then they'll say, all right, now let's see, I'm trying to find out DF, and DF corresponds to JL, which means DF must be 1.61 repeating times bigger than JL. And so then they'll reach for their calculator and they'll put 325 times 1.61111111. And if they use as many ones as the calculator would allow them to use, then they will get a correct answer. If they do any rounding, they're going to be in trouble, okay? So that's kind of the intuitive way to do this problem, okay? But again, if you don't learn and adopt the habit of writing ratios and setting those ratios equal to each other, you're going to find some problems to be impossible to solve by this kind of intuitive way. Okay, let's move on and do a second problem, which is really very, very easy. The homework actually starts with a couple of problems like this one, number 2 here. Again, 2 triangles are similar. I've given you the order of the letters and the names. Find the measures of angles C and D. Well, angle C must correspond to angle A from the other triangle. All right. And then angle D must correspond to angle B from the other triangle, okay? So I'm looking for angle C. C corresponds to A. What is angle A? Angle A is 62 degrees. I should do that in red. And so angle C is also 62 degrees. 62 degrees. Notice I wrote 62 in the diagram, because if you don't write 62 in the diagram, and you're not necessarily going to know this going into the problem, okay? But when we go to find the measure of angle D, which we have decided corresponds to angle B, all right, D corresponds to B, but I don't have a measure for B. But I can get a measure for B because I have discovered the measure for angle C. So subtract the 65 and the 62 from the 180, and we will get 53 for angle B, and that means then that angle D must also be 53 degrees, okay? And again, the principle being that when figures are similar, all the corresponding angles must be exactly the same. No change in angle measures at all, okay? So it's pretty simple. Now, number 3. There's more than one complicating factor to this problem. The first of which is I haven't given you a similarity statement. I haven't named the triangles, and I haven't told you the order in which things correspond. Okay? And this is critical. We must know which things correspond to which things to get the ratios right and to get the math right. Okay? In fact, without a statement telling you that the triangles are similar, how do we even know if the triangles are similar? Okay. Well, here's how we know. You see the parallel line marks in this figure? Remember what that means? When you have a transversal like this one connecting two parallel lines marked by the arrows there, that means these angles here, we have a name for them, they're called alternate interior angles. We didn't quiz or test you on that last semester, but you might remember that phrase. Alternate because they're on opposite sides of the transversal, and interior because those angles are in between the parallel lines as opposed to outside of the parallel lines, right? You got parallel lines connected by a transversal. You got two acute angles there. They must be congruent to each other, okay? So those angles are congruent. And then once again, you've got, I should highlight those two parallel lines again. You've got this transversal over here connecting those parallel lines, which means this angle must be congruent to that one down there. Okay? So I've got two pairs of congruent angles there. And clearly, these vertical angles must also be congruent. And so now I know how all the angles correspond to each other. And I strongly suggest that what you do when you encounter a problem like this, which you will on the homework, is that you write out names for the two triangles with the letters in corresponding orders. So it doesn't matter what you call the first triangle. I'll call it PQV. You could have called it PVQ. It doesn't matter. But what does matter is how we name the next triangle. Angle P corresponds to angle Z. Angle Q corresponds to angle W. And then finally, angle V corresponds to angle V. Okay, so now I know how the letters match up. Now I know how the sides match up. Okay, trying to find the value of X. X comes from side WZ. Now, probably without doing this work here that I urge you to do, you would probably all guess that that X corresponds to the 86, and you would be right. And we could verify that by looking at the names of the triangles that I've written. The X comes from segment WZ. That corresponds to PQ, which is the 86. Okay, and again, I'm going to do this problem by setting up ratios, not by this intuitive method of figuring out which triangle is bigger, figuring out how many times bigger, and then multiplying, some small number by that amount. Again, you can get away with that for some fairly easy problems, but eventually that method is going to leave you stranded. Okay, write ratios. X corresponds to the 86. But here's what a lot of people will get wrong if you're not careful about the triangle names. I only have one other segment from the small triangle where the X is, and that's the 75. Okay, so let me highlight that. Now, which segment from the big triangle does that 75 correspond to? Okay, without naming the triangles, going through the careful analysis of matching up the congruent angles properly, naming the triangles properly in a corresponding fashion, a lot of people will make the mistake of putting the 75 over this 60. And that's just wrong. And we can check that that's wrong, again, by going to the name. 75 comes from segment VZ. Where's VZ? VZ. Those two letters in that triangle name. What does that correspond to? It corresponds to VP from the other triangle. That's the 92. Okay? So there's the correct equation. If you use a 60 anywhere in your work for this problem, you're going to get the wrong value for x. Okay. And again, solving this equation, super easy. Multiply both sides by 86. Okay. Pick up the calculator, do the math, you get your answer. Again, the correct answer will be in the completed version of these notes. All right. Here's the other thing that concerns me about the intuitive method, okay, which I'm talking so much about because I'm trying to warn those of you who are inclined to ignore my way of doing these problems. Those of you who like to use the intuitive method, even if you got the 75 corresponding to the 92 correctly, okay, what you are likely to do is you're likely to divide the 92 by 75 rather than the other way around, the way that I've written it here, 75 divided by 92, because people like to divide larger numbers by smaller numbers. It's just kind of an instinct. It's a natural inclination. They'll divide 92 by 75, and they'll get something like 1.17, something like that. And then they'll go, okay, so it's 1.17 times bigger. And then they'll look at the 86, and they'll multiply the 86 by 1.17 and get some answer that is bigger than 86. But you see, this triangle down here is the smaller of the two triangles. The answer should be less than 86. And some people will just not, they won't notice that. They'll be too careless. And they'll come out with an answer of, 100 and something, and it won't ever occur to them that that can't possibly be right. Okay? Now, what you could do, and if you're really on your toes, is you'd realize, oh, I need to divide the 86 by 1.17. And if you did that, you would get the correct answer. Okay. But already, I hope you're beginning to appreciate that this intuitive way of going at these problems has its drawbacks. And now when we get to this next problem, it's really going to leave you high and dry. Okay. If you refuse to try to do what I'm encouraging here, write two ratios, you're going to be stuck for this problem. Trust me. So let's look at problem number 4. Let me get some of this stuff out of the way. All right, once again, no statement about triangles being similar. So I'm going to need to find angles that are congruent to each other so I can match these two triangles up so that I know the triangles are similar. Well, again, I've got parallel lines here. And here's a transversal over here connecting these two parallel lines. So this acute angle and that acute angle must be congruent to each other. And then here's a different transversal connecting those two parallel lines. So those two acute angles must be congruent to each other. And by the way, you see the two triangles in this diagram, don't you? Triangle JVK, the one on the top, and then triangle JTA, like the whole thing, right? I've got two pairs of congruent angles in those triangles, and not that I need it now, but because if you've got two pairs of congruent angles in two triangles, then the third pair of angles has to be congruent because the triangles always add up to 180, right? The angles always add up to the same total. So if you've got two pairs that are congruent, how could the third pair not be congruent? Okay. Nonetheless, let me just show you here that both the little triangle up top, JVK, and the whole triangle, JTA, they both share angle J. It's the same angle in both triangles. So we got three pairs of congruent angles. Again, I'm going to name the triangles here, triangle JVK, and I'm going to erase some of that work there again so you can see the names in the letters in the diagram clearly. JVA, similar to, well, let's see, that angle was congruent to itself. That one was congruent to that one. That one was congruent to that one. So let's see, the J corresponds to itself. The V corresponds to the T. And then JVK, the K corresponds to A. Okay, I've got the triangles named properly. I know they're similar because all of the angles are the same. Okay, and by the way, if you've really been thinking, you might have this question looming around somewhere in your head and saying, wait a minute, Mr. Nartillo, how do you know just because all the angles are congruent, that the figures must be similar and that all of the side ratios must be the same. And if you've been wondering that, I'm going to kind of dodge answering that question and say we just know. Okay. Yeah, I'm just going to dodge and say we just know. If you know that all of the angles, all the pairs of corresponding angles are congruent, that's enough in triangles to know that the triangles must be similar to each other. Okay. So then we have the right to go and set up these ratios and find the lengths of sides. So I'm looking for X, and X corresponds to segment JV. Do you see that? X corresponds to the JV. So I'm going to start a ratio with an X, and what does that correspond to? Not 3. I mean, if you're thinking the X corresponds to 3, segment JV corresponds to segment JT. How long is segment JT? You can't give me a number answer for that. You got to give me an algebraic expression. The length of JT from this point all the way down to that point, it's X plus 3. Okay, so there's one ratio. Now, that must be equal to any other ratio that I could build from these two triangles. So let's go back to the first triangle, JVK. Do I have another side of JVK? Well, yes, I do. I've got this 16 here. Okay, that comes from segment VK. And that corresponds to TA, which is 20. Okay. Setting up these ratios is the only way you're going to get the answer to this question. Okay. Because if you do it by the intuitive way, and if you're astute enough to recognize that 20 corresponds to the 16, and you do 20 divided by 16, and you get 1.25, and then you say, well, it's 1.25 times bigger, so I guess I better multiply something by 1.25 to get the X. Are you going to get a way wrong answer? You could do that, and you'd probably multiply the 3 by 1.25, and you'd get 3.75. Now look at this picture. If this is 3, does that X look like 3.75? This is not a badly drawn picture, okay? 3.75 looks way off, doesn't it? Doesn't it look like that X is more like about 9 or 10 or something in that range? Okay. The only way you're going to get this problem right is to set up the ratios. Okay. Now the algebra for this is a little bit more involved. Okay. But you've done this algebra. Okay. When you've got two fractions set equal to each other, we can cross multiply. In other words, multiply let me just change the color here, the X times the 20 and the 16 times the X plus 3, and set those products equal to each other, right? So we've got 20 times X is equal to 16 times X plus 3. Oh, I've made a serious mistake there when I wrote that down. Do any of you understand, realize what it is? Need parentheses around the X plus 3 because you're multiplying 16 by all of that, not just by the X. Okay, so now distribute the 16. 20x is equal to 16x plus 48. Now subtract the 16x. And we get 4x is equal to 48. Divide both sides by 4. X is equal to 12. Okay, I was estimating 9 or 10. 12 is not that far off, but 3.75 looked bad and it would have been way off. Okay, you've got to set up the ratios. And to set up the ratios correctly, you've got to name the triangles properly. And to name the triangles properly, you have to identify pairs of congruent angles. Are you listening? This is where it starts for many of these problems, certainly the more complicated ones, and you're going to have to do plenty of them. You've got to identify pairs of congruent angles. Okay, let's move on to two other problems where you have to do this sort of thing. Number 5, I got a couple of parallel lines there again, and so I've got a transversal here connecting those two parallel lines. That means those two acute angles are congruent. And then I have a different transversal connecting those two parallel lines down there, which means these acute looking angles, I don't know, they might be obtuse looking, but for sure they've got to be the same. Okay. And then there's two triangles in this picture. I'm sure you see them both. And I think you can see that they both share angle L. Okay. Well, now that I know where the congruent angle pairs are, I can name these two triangles. Right. So let's name the big one first, but it doesn't matter. SCL. Okay. Triangle SCL is similar to. Let's see. The S matches up with the M. The C is congruent to the I, and then the L matches up with itself. Okay? Once again, listen to me. You cannot write the equation properly until you write out the names of the triangles, and you can't do that until you identify congruent angle pairs. That's where this problem starts. As soon as I go through this lesson and I ask students to try this problem, student calls me over, they're looking at a problem like number 5 and they're completely stuck and they say, Mr. Nortilla, how do you do this? I don't know how to do this. How do I do this? My answer is you've got to start identifying pairs of congruent angles. You see the parallel lines? That's a clue. Okay. So I'm looking for the value of x. This problem is even more complicated. Wait till you see why. Because, let me erase those transversals there. That x comes from segment CI. Okay, I want to change that color, CI. I'd like to start my equation with that x, but CI is not a side of a triangle. I mean, look at this triangle name. There's no CI in there. There's no CI in there. I cannot use x by itself in this equation because x does not represent a full side of either of the triangles in this picture. In these equations that I've been setting up with a fraction on the left and a fraction on the right, every spot in that fraction, all 4 locations, must be representing a full side of the figure. Okay? And x does not represent a full side of either figure. So, does that mean we can't do this problem? No. Okay. It means we need to find a full side of one of the two triangles where the x is at least included. And the x is included in this whole side of the big triangle SCL, right? But the length of that side is not x, it's x plus 33. Okay? That's the length of segment CL. And what does segment CL correspond to? Going back to the names that I wrote. And where did I get those names? From the congruent triangle pairs. CL corresponds to IL. And how long is IL? Look at the diagram, it's 33. Okay, so there's one ratio. Now I need another ratio. Okay, and you got to be careful here. The x plus 33, this numerator came from the big triangle, the first one, SCL. So now I need a number up here also from the big triangle SCL. Well, I only have one number to draw from, and that's this 18. And that corresponds to, or that comes from SC which corresponds to MI, which is 15. Okay, there's a good equation. Once again, if you're relying on the intuitive way of doing a problem and trying to apply that to this problem here, you're almost guaranteed to get stuck, lost, frustrated. Okay, identify the congruent angles, name the triangles, set up ratios equal to each other. Right, now, how would I solve this problem algebraically? Well, I would multiply both sides by 33. That's what I would do. I wouldn't cross multiply. You can, but it's just going to create extra work for yourself. And I know students love to cross multiply because they're familiar with it. They find it easy to do, but I wouldn't do that. I would multiply both sides by 33. That will cancel out that 33. Okay. And I don't know, can I do this in my head? 1 1/6. I think 18/15, which is 1 1/5 of 33. So 1/5 of 33 is going to be 6.6. So that's going to get me 39.6 on the right. Okay. X plus 33 is equal to 39.6. I hope I have that right. If I made a mistake, it'll be corrected in the completed version of these notes. Well, now just subtract 33 from both sides, and you get x equals 6.6, which looks reasonable in the diagram, doesn't it? Okay. 2 steps algebraically is all it took me to solve this problem because I didn't cross multiply. Okay. And again, I'm not gonna criticize anybody for doing this different algebraically from me. You want to cross multiply? Fine. That's going to be 1 step. Then you're going to have to distribute. That's 2 more multiplying steps. Then you're going to have to do 2 subtractions to eliminate terms. That's a 4th step, a 5th step, and then finally divide a 6th step. It's going to take you to do this problem if you insist on going the cross multiplying route rather than doing it the way I've done it, which you can do it. It's your time. Okay. All right, number 6. This one is the trickiest one of all for sure to get the angles marked correctly, the triangles named properly, and the ratios set up properly. Okay. I have 1 pair of congruent angles already marked in the picture. There are no parallel lines in this picture, but you do see the 2 triangles, right? This little triangle in the upper left, BLR, and then the big triangle, BTY. All right. I need to identify at least one more pair of congruent angles. Okay. I know that angle R in this little triangle corresponds to angle Y in the larger triangle. And you might be able to judge visually where there's another pair of corresponding angles. Okay. But I think what's clear here is that angle B is part of the little triangle BLR, and angle B is also part of the large triangle BTY. It's the same angle B. It's congruent to itself. Just like over here in this problem, angle L was congruent to itself. And in the previous problem, the one before that, here, this angle up here, angle J was congruent to itself. In this case, I wouldn't say angle V was congruent to itself. You had 2 different angle V's there, but they were vertical angle partners. Okay. That angle B is congruent to itself. That acts like a pair of congruent angles. And again, once you got 2 pairs of congruent angles in triangles, we know the 3rd pair has to be congruent. So I don't even need to justify the 3rd pair. I know now the order of the letters. So I'll name the first triangle BRL. But again, that order doesn't matter. What matters is I get the next triangle name right. And in the big triangle, what corresponds to the B? Well, the B itself. Okay. BRL is the little triangle. Angle R from the little triangle, that corresponds with angle Y in the big triangle. And then angle L, that's this last one here in the little triangle, that must correspond to angle T, is the only other angle name left for the big triangle, BRL similar to BYT. If you don't identify the congruent angles, you don't get the names right, and you will not get the ratios right. Trust me. Okay. Now, what does the X represent? It represents TY. And the TY comes from here. That must correspond to the LR, which is how long? LR in this diagram is 20. Okay. Now I need another ratio. I need a numerator that comes from the same triangle that the X came from, which was this one over here. Let's see. Do I know BY or do I know BT? I got to know one of those two. Let's see. BY is 24 plus that 36, which is 60. The BT, I don't really know the length of that. It's 30 from B to R, but then I don't know how long it is from R to T. So I'm going to have to use BY, which is the 24 plus the 36, which is 60. So BY corresponds to BR. And how long is BR? BR is 30. Okay. Now, as it turns out, the math here is super easy. You could probably do this in your head. Okay. But again, getting the equation set up properly, almost guaranteed to fail if you don't follow the approach that I have been trying to pass on to you. Okay. So multiply both sides by 20 here. Final answer, X turns out to be 40. Okay. Last problem. There is a problem like this one in the homework too. There's a word problem here. It says a 5-foot girl standing outside casts a 32.6-foot shadow at 6 p.m. on a summer day. Wow, lots of numbers there. What does this have to do to similar figures? Well, let's draw a little picture here. You got a 5-foot girl. We're going to assume for this problem she's standing straight up, okay, and that she's standing on flat ground, and that her shadow is 32.6 feet long. That's what it says. And so that there is a right angle between, her stance and the ground. Okay. At the same time, a high-rise building she's standing next to, a high-rise, very tall building, casts an 875-foot shadow. And we're going to assume that building is standing straight up, that it is not the Leaning Tower of Pisa or any other such thing. Whoops, I put the 875 in the wrong spot. 875-foot shadow. We're asking how tall the building is. Okay. Well, we're going to solve this problem by adding a little bit more to the picture to make it a familiar looking type of problem. We're going to draw in a third segment in each of these to create a complete triangle. That third segment kind of representing, let's say, the ray of sun that is coming from the west. Okay, and over this girl's head and the rooftop and casting the shadow on the ground. Okay, and we're going to set up ratios, do a little algebra to solve for the length of X. But again, only if we know that the triangles are similar. And the only way we know the triangles are similar for sure is if we have at least two pairs of congruent angles. Right now, we've only got one, and we've kind of even assumed that one because we assumed that the girl in the building are standing straight up, but that's a fair assumption to make for this problem. How do we get a second pair of congruent angles? From the context of the problem, okay? These shadows are both being made by the sun at the same time of the day, in the same general vicinity, okay? So if you think about it, if you think about looking up at the sun from this point on the ground, you might measure the angle off of the ground up to the sun, and it might be 15 degrees or something like that. Wouldn't the angle up to the sun from this point on the ground be the same? Right? I mean, the sun's in the same place in the sky for everybody. For the girl, the building, the trees nearby, the sun is up at the same angle, no matter where you're standing or how tall or short you are. Okay, so that's how we get a second pair of congruent angles, and then we know the triangles are similar to each other, and now we can set up this ratio. The X corresponds to the 5, and the 875 corresponds to the 32.6, so 875 over 32.6. Very easy algebraically to solve. Just multiply both sides by 5, pick up the calculator, plug that in. whatever the answer comes out to be, it comes out to be. The notes will have a completed answer. Okay? Get after the homework.